All right, let's get started. Welcome, everyone. Today we are going to start off by doing an example from the multinomial distribution, and then we'll segue into the bivariate normal distribution. As far as announcements go, exam 3 is a week away, so that will be the same procedure as for our first two exams. There will be an in-class portion, that's a Canvas quiz, probably be one multiple choice question at the start, and then some problems where you'll write your work, take a photo of it, and then submit it. And then a take-home portion where you'll be working in R to solve a problem that will be untimed. There is a practice exam up on Canvas. Because you've now done this twice, I did not bother putting in the work to make the practice exam into a Canvas quiz. It's just a Word document that contains a bunch of practice problems that I think will be helpful to you as you prepare for the exam. Are there questions about exam 3? All right. Something else that I should mention is that math retreat is next week. So I encourage you to attend your friends and classmates' talks at that. And I encourage you to sign up to participate in the math retreat competition. That's on Wednesday afternoon. Currently, I heard there's only one team registered. So if you sign up, there's a pretty good chance that you would win a prize. Teams of 3, and you can sign up by emailing Dr. Walker. And I think you can also email her if you want to participate but don't have a team yet, and just ask her to pair you up with someone else who also wants to participate. All right. So last time we talked about the multinomial distribution. And we used an example of low risk, medium risk, and high risk drivers to prove what the covariance of two random variables that are part of a multinomial distribution should be. So let's take a look at this example. Let's suppose that 50% of the population is low risk, 30% is medium risk, and 20% is high risk, and that they get charged different fees by their insurance company based on their level of risk. And let's suppose that an agent sells policies to 4 new drivers that have independent risk categories. And we want to find the expected value of the total fee from the 4 drivers. So try writing down in terms of symbols what it is that we're trying to find. Like, don't try to solve it yet, just write down what our goal is. So here we have a fixed number of trials. We have 4 drivers. We know that each of the trials is independent. And then we have more than 2 possible categories that each trial can fall into. So we have 3 risk categories that each driver can fall into. And their probabilities add up to 1. So if we have a random variable for the number of low-risk drivers in this group of 4, the number of medium-risk drivers, and the number of high-risk drivers, those 3 random variables together have a multinomial distribution. So what we're looking for is the expected value of the total fee, which is going to be $200 was the fee for the low-risk drivers, so 200 times however many low-risk drivers there were, plus 400 times however many medium-risk drivers, plus 800 times however many high-risk drivers there were. So what do you think our strategy is going to be to find this expected value? Yeah, we can split it up across the addition and pull the constants outside using the same techniques that we've been using all semester long. That to use those techniques, we don't need the random variables to be independent. So we have 200 times the expected value of y sub l plus 400 times the expected value of y sub m plus 800 times the expected value of y sub h. What is the expected value of y sub l going to be? Exactly. Remember that when we're finding the expected value of multinomial random variables, we focus on one of the categories, say low risk, and by grouping together everything else into not low risk, we're now dealing with a binomial random variable. So the expected value is just n times p for that category. So when we multiply these out and add them up, we end up with 1,520 as the expected value of the total fee from the 4 drivers. A nice sanity check on this is to divide that by 4, and we get an average of $380 per customer. And looking at that, that seems about right. That makes sense that it should be in the range 200 to 800, but closer to 200 than to 800 because there are more low-risk drivers than high-risk drivers. Questions about this part? All right. So now let's find the variance of the total fee. So we're finding the variance of the 200YL plus 400YM plus 800YH. And for this, we can use our table approach because we want the variance of a linear function of 3 random variables. So start by filling in this table with just the covariances. So we're not looking at the coefficients yet. So recall that the covariance of a variable with itself is just the variance of that variable. And again, thinking about this as a binomial random variable, the variance of y sub L is going to be n times p times q. So n times the probability of a low-risk driver, which was 0.5, times 1 minus the probability of a low-risk driver. And then for the non-diagonal entries, we have the covariance, say, of y sub L and y sub m, which is what we proved yesterday as being negative n times p sub L times p sub m. So use those two structures of formulas to find the covariances. All right. So for example, in this upper left cell, we have 4 times 0.5 times 0.5, so a variance of 1. And in this next cell, we have negative 4 times 0.5 times 0.3, so negative 0.6. Remember that covariance matrices are symmetric across the diagonal. So our covariance of y sub L and y sub m is the same as the covariance of y sub m with y sub L, so also negative 0.6. So when we fill the rest of those in, that's what our covariance matrix ends up looking like. What's our next step going to be? If our goal is to find the variance of this linear function. Kyle?
When you're finding the coefficients.
Yeah, now we're going to write in the coefficients next to the appropriate random variables and multiply them inside of the table. So for example, this upper left-hand cell becomes 1 times 200 times 200. And this cell in the top middle becomes negative 0.6, which was the covariance, times 200 times 400. So the two coefficients in that row and column. So then the variance of the total phi, the variance of this linear function, is the sum of the entries in this table. And that ends up being 206,400. Are there questions about this? Folks online, any questions about this? Nope. All right. Well, in that case, let's switch over to the bivariate normal distribution. All right, so to refresh your memory, recall that the density function for a normal distribution for one variable looked like this. You had 1 over the standard deviation sigma times the square root of 2 pi times e raised to the power of -1/2 times x minus mu, where mu is the mean quantity squared, divided by the variance, or the square of the standard deviation. The bivariate normal distribution is a normal distribution for 2 variables, and its density function looks like this. So you'll notice we have a lot of the same structure as we had for 1 variable. We still have 1 over the standard deviations. Just now we have 2 standard deviations, one for x and one for y. Instead of the square root of 2 pi, we have 2 pi. That kind of makes sense if you think about multiplying the square root of 2 pi from x and the square root of 2 pi from y. And then we have this additional factor of the square root of 1 minus rho squared, where rho is the coefficient of correlation between x and y. So here we're using z here to sort of compress this more complicated function of x and y. So for each of the 2 variables, we have the variable, say x, minus its mean, quantity squared, divided by the square of the standard deviation. So we have that for x and y, and then we have minus this term in the middle. That's a function of both x and y. So if you think back to a normal distribution for 1 random variable, you know that the density function, little f of x, has this bell-shaped curve. So the density function, little f, is controlling the height of this curve, where this is saying that values where the curve is higher are more likely. So you can think about generating a bunch of random values from this distribution, They would be sort of clustered here in the middle, and then you'd have a decreasing chance of getting something out in the extremes. For two random variables, the thing to think about is the density function being the height of a surface. Think of it as the height of a hill, where if you look at it either standing on the x-axis or standing on the y-axis, sort of its one-dimensional cross-section looks like a bell shape. And then the height of the hill is telling you how likely points are to fall in that region. So near the sort of peak at the center of the hill, values are more likely to happen for those values of combinations of x and y. Everybody kind of got a mental picture of what this density function is doing for us? Kind of. All right. Oh yeah, and just like the regular normal distribution, this is valid for values of x and y anywhere between negative infinity and infinity. Okay, so here's what this looks like when we generate random values from this distribution. So when rho is 0, so the correlation between x and y is 0, our hill is sort of like, it's still bell-shaped, but it's sort of squared up. It doesn't have a tendency to angle in one direction or another. So our random values form this random cloud of points with no upward or downward trend in them. When the coefficient of correlation is 0.7, we get a hill that's sort of positioned at an angle, so that if y is bigger, x is also likely to be bigger. And if rho is, say, negative 0.28, a negative value means our hill is positioned at an angle, going the other way, so that if y is bigger, x tends to be smaller. But because this correlation coefficient is closer to 0, we're not as tightly constrained towards the line. So 0.7 gets us a pretty clear boundary of an elongated ellipse. With negative 0.28, it's a bit more like sort of the random cloud, but with a bit of a tilt to it. All right. So the marginal distributions of x and y, if x and y are bivariate normal, then the marginal distribution of x is normal with mean mu sub x and standard deviation sigma sub x. And similarly for y. So I told you that if you're standing on the y-axis and looking at this hill, the cross-section looks like a bell curve. This is what I meant by that. The marginal distribution is a normal distribution. We're not going to go through the proof of this, but there's a link to a nice proof of this here. So for example, where this could be useful would be the returns of two stock mutual funds in percentages are bivariate normal with these values for mu sub x, mu sub y, the standard deviation of x, and the standard deviation of y, with a coefficient of correlation of 0.5. And we want to find out what's the probability that fund Y will give a negative return? So take a moment to think about how you're going to approach this problem, and then we'll talk about it. So the idea here is that we're looking for the probability that Y is less than 0. So we don't actually care about X, we're just focused on Y. But we know that the marginal distribution of Y is that it's a normal distribution with a mean of 8 and standard deviation of 5. So we can find the probability that Y is less than 0 using our same techniques that we had from chapter 4 for working with a single normal random variable. So if we want to solve this using a table, we would start by converting it into a standard normal distribution. So the probability that Y is less than 0 is the same as the probability that Z is less than 0 minus the mean divided by the standard deviation. And then use a table to find the probability that Z is less than that value, so negative 1.6. So that's the same as the probability that Z is greater than positive 1.6. So that's 1 minus the probability that Z is less than 1.6. So let's go on to our table. So we want to locate 1.6. So 1.6, 0. So 1.60. Probability of being less than that is 0.9452. So we have 1 minus that gives us 0.0548 is our probability that fund Y gives a negative return. Alternatively, if you happen to have a calculator handy, you can use normal CDF to find the probability that Y is between negative infinity and 0 using its mean and standard deviation. All right. So I would like to take a moment to show you how to simulate this. We have some code on Canvas. So bivariate normal.r is the R code that I'm going to be showing you here. This is working with the mass package. So the first time you use this on any given installation of R, you need to install it. Let's see if it's already installed on this computer. Yes, so that looks good. So the way we can simulate this is I'm going to put in a vector mu with the means of x and y. And then a matrix sigma. So this is going to hold the values 9, 7.5, 7.5, 25 with number of rows equal to 2. So here's what that looks like. So the diagonal elements are the variances. So 9 is the variance of x, right? Because we had that the standard deviation of x was 3, so 3 squared. Standard deviation of y was 5, so we have 25 for the variance of y. And then the off-diagonal elements are the covariance of x and y. So remember that that's going to be the product of the standard deviations times the correlation coefficient. And then we can use the MVR norm function to simulate values from a multivariate normal distribution. So I'm going to simulate 10,000 values. And then here I'm just looking at the first 10 rows of them. So here we got x was equal to 1.3 and y was equal to 10.7. Then the second row, x was equal to 9.97, y was equal to 12.3, and so on. So if we plot these, we get this scatter plot showing us the relationship between x and y. And we see that they are, in fact, positively associated, which agrees with the fact that we simulated them to have a correlation coefficient of positive 0.5. So then how can we use our simulation to check our answer to our probability that fund y will give a negative return? So we found the theoretical probability that y would give a negative return. How can we find the empirical probability? Kyle?
When you just do it, so every time that the y value was negative, you just add, take like the counter and just end up dividing the success rate of whatever that was by the non-times generated number.
Exactly. We'll count it as a success every time y was negative, and then divide by the number of simulations that we did. So you could do this using a for loop, but in this case, we can actually do it faster because we generated 10,000 numbers all at once, or 10,000 pairs of numbers rather. Here we have stock square bracket comma 2 is taking the second column of our stock matrix. So those are our y values. We're checking if that's less than 0. So remember, this is going to create a vector of trues and falses. So it's going to be true in every row where y is negative. And then we'll take the sum of those. So that's going to count each true as a number 1. So this sum is going to be the number of rows that had y less than 0. And then we'll divide by 10,000. Questions about that? So then what we're hoping is that this is going to give us an answer close to 0.05. So close to our theoretical probability. There we go, 0.0562. Questions about this? If we want, we can also make a histogram of the y values. So using the hist function, make a prediction in your head about what this graph is going to look like. Ta-da! So this looks like a normal distribution. That's good because this is the distribution of y. And we said that the marginal distribution of y was a normal distribution with a mean of 8. So that looks about right. It looks like it's centered around 8. All right. So another useful fact about bivariate normal distributions is that if x and y are bivariate normal, then any linear combination of x and y is also normal. So for example, taking our stock example, suppose that 80% of your portfolio is in fund X and 20% of your portfolio is in fund Y. We want to find the probability that your weighted average return is negative. So in other words, we're looking for the probability that this new random variable u, that's 0.8 times x plus 0.2 times y, we want the probability that u is negative. Well, we know from this important fact that u has a normal distribution. And we can find its mean using our old friends, the important facts about expected value. And then we can find its variance using our table method that we had from linear functions of random variables. So let's try this. Why don't you start with just finding its mean? So we had u is equal to 0.8x plus 0.2y, and we can back up to go back to our values of mu sub x and mu sub y. So the mean of x is 5, the mean of y is 8.
Are we trying to find the x and y?
So you're trying to find the expected value of u, where u is 0.8 times x plus 0.2 times y.
Okay.
Oh, I didn't need to back up. I had some mean summarized here. So the expected value of u is the expected value of, oops, that should be 0.8, not 8. So we have 0.8 times the expected value of x plus 0.2 times the expected value of y. And then we're filling in mu sub x and mu sub y for those expected values. So we have 0.8 times 5 plus 0.2 times 8, which is 5.6. So that's our mean for the normal distribution of u. And then we want the variance, or the standard deviation. So, whoops, did those in the wrong order. So to do those, we start by writing out our covariance matrix. So again, we have standard deviations squared for the variances. And the covariances are the standard deviation of x times the standard deviation of y times the coefficient of correlation. And then we're going to fill in the coefficients, because this is u is a linear function of x and y. And then the sum of this table is the variance of u. So that ends up being, the variance of u is 9.16. So the standard deviation of u is the square root of that. And now we know the distribution of u. We know that it's normal, we know its mean, we know its standard deviation. So now we can either use normal CDF on a calculator, or we can use a normal probability table to find the probability that u is negative. So here's what that looks like. Either using a normal probability table, we translate it into a standard normal distribution and manipulate it so it's a value we can compute from the table, or we use normal CDF of the probability that u is between -infinity and 0 and put in its mean and standard deviation. Questions about this? Folks online, any questions? All right. We can also think about the conditional distributions of x and y. So the conditional distribution of x, given that y equals some specific value little y, is a normal distribution with this expected value. So we have the mean of x plus our correlation times the standard deviation of x over the standard deviation of y times y minus the mean of y. And variance equal to the variance of x times the quantity 1 minus the square of the correlation. So in other words, if we know the value of y, the variance of x gets reduced because we know something about x based on knowing y. So we square the correlation, 1 minus that, so this is our reduction factor for the variance based on knowing something about y. And you can see that the more strongly x and y are correlated, either close to +1 or close to -1, the more the variance gets reduced by knowing the value of y. And notice what's going on with this expected value. Let's say that the correlation of x and y is positive, and let's say y is greater than its mean. In that case, this term that we're adding to the mean of x is positive, right? Because the standard deviations are always positive. So if y is greater than its mean, then we expect x to be greater than its mean if x and y are positively correlated. So that agrees with our intuitive understanding of what it means to be positively correlated. That works out in the numbers of what is the expected value of x, given that y equals y. And the opposite is true if y is less than its mean, and they're positively correlated, then the expected value of x is greater than its mean. Or if y is greater than its mean, but they're negatively correlated, then we expect x to be less than its mean. Questions about this? All right. Thank you all for your attention. I will see you on Thursday for conditional expectation.
Thank you, Doctor.
Thank you. You're welcome.